Hi everyone, welcome back to another module for Kines 7103. Today we're going to be talking about the normal distribution and the t-distribution, and how if we know the underlying distribution or can make some assumptions about the underlying distribution, that then we can use those distributions to calculate the probabilities of observing certain events. So we can find the probability of an event under the normal distribution, right? And this is not unlike other probabilities that we've solved before, where, if we think about like rolling a die, we could say on a fair die, all outcomes are equally probable. But if we're talking about the likelihood of something else, like for instance, getting an intelligence test score above a certain value, we need to know something about the way that intelligence test scores are distributed, right? On things like fair coin flips or fair die rolls, each outcome is equally probable. So there's a uniform distribution where you have a flat probability density function. But for a lot of things, as we've discussed, you'll get something that approximates more of a normal distribution, right? It has this bell curve. So intelligence test scores are a useful one in this regard because they are designed to have a mean of 100 and a standard deviation of about 15, which means the bulk of the data, right, are between 85 and 115 as you go one standard deviation in either direction, and then you get less and less or fewer and fewer observations in those tails as you go out in either direction. So we can then say that this represents an approximately normal distribution, or in this case I've simulated it to be a normal distribution, but if we can say it's at least approximately normal, what is the probability of observing an event of an IQ score of 130 or greater, right? So we're going to say at 130, what proportion of the data are to the right of that cutoff? What is the probability of getting an IQ score of 130 or greater? Now, if we had all these data, right, if these were actually data that we had collected, or if this was like a census kind of thing that was taken, we could calculate this probability empirically. We would just count the number of observations that were equal to or greater than 130 and then divide by the total number of observations. If we didn't actually have access to all that data, or for instance, we wanted to take like a bit of a shortcut, you could do this in a theoretical way. So if we know that the underlying distribution here is normal, rather than having to count all of the individual observations and then divide by the total number of observations, what we can do is we can integrate this total curve to find the area under the curve, and then compare it to the area just under this part of the curve if we truncate it at 130. We can then say, okay, well, what proportion of the scores would be greater than or equal to 130 in a normal distribution? So being able to approximate these things theoretically is especially useful because a lot of things in nature follow normal distributions, or at least approximately normal distributions, right? For instance, one of the things we talked about was linear combinations of random variables, right? If I add a lot of random variables together, most of the time we're going to end up with a normal distribution where we have a lot of scores of the average value, but extremely small scores or extremely large scores become less and less likely, because in order to be an extremely large score on a combination of random variables, that means you had to have large values on each individual variable, which is unlikely, right? Whereas most people are going to have some mix of large and small values, so most of our values would end up in the middle. Or if you were thinking about it on the other end of the tail, right, in order to get a very small score in a combination of random variables, you would have to have a small value on each of the variables, which is also going to be unlikely. So we're going to get fewer and fewer scores in the tails of this distribution. But now that we can say that this is approximately normal, or in this case it is truly a standard normal distribution, we can actually derive this probability mathematically from the mathematical description of a normal curve. So what we need to do first is actually convert our observed score, x, into a z-score, right? And a z-score is defined as x minus the mean divided by the standard deviation. So we can do that to then say how far above the mean is x in units of standard deviation, right? So if we have IQ scores that have a mean of 100 and a standard deviation of 15 and our x is 130, we have 130 minus 100, which we divide by 15, and that's going to give us a z-score of 2. So we can actually draw our cutoff now, rather than at 130 IQ points, we can draw that cutoff at 2 standard deviations. And if we draw that cutoff at 2 standard deviations, what we can then do is actually say, okay, given the mathematical description of the normal distribution, what is the area under the curve at 2.0 or greater compared to the total area? And that will give us the proportion of the curve beyond that 2.0, right? So we can kind of write this as a shorthand, is we're going to get the probability under the normal curve for 2.0. And specifically, we're talking about the probability in the tail here. So this is the lower part of the distribution over here, and this is the upper part. So the lower tail would be everything to the left of this cutoff. The upper tail is going to be everything to the right of this cutoff. So these are just complementary probabilities, right? But in this case, the upper tail is what we're interested in because we want to know if it's 2.0 or greater, and we'll find that will happen 0.023% of the time, or 0.023. So about 2%, 2.3% of the time is when we'll actually get a score of 2.0 or greater. So that's a fairly unlikely event under a normal distribution. Now, we can also extend this idea to, rather than talking about the probability of observing a single score, we can talk about the probability of observing a sample mean. Because if you recall from our previous lectures, we talked about how a distribution of sample means is approximately normal, and that this is going to be true even if the parent distribution is not normally distributed, right? So even if the distribution that generated our sample isn't normal, if we're talking about the sample means, we would expect to get an approximately normal distribution of sample means, and we expect this to become more normal the larger our sample size gets. Now, if we had a normal distribution to begin with, the distribution of sample means will be pretty normal at small sample sizes. But if we have a very abnormal distribution, or non-normal distribution, I should say, what you're going to get is a less normal distribution until your sample sizes start to get pretty large. But as our sample sizes get large enough, we know we're going to hit a normal distribution regardless of what the parent population looks like. And this is great because it allows us to calculate the probability of observing a sample mean in a very useful way. So for instance, if let's say our hypothetical intelligence test scores are distributed very differently. Let's say that rather than normally distributed, we're going to have a uniform distribution of intelligence test values. So every intelligence test score from 0 to 200 is equally probable. And this is not at all how these things are distributed, but we're doing this specifically to show you that if you sample and calculate sample means, they are going to approximate a normal distribution. So from this population, I took 10,000 samples. I took 10,000 samples when the sample size was equal to 10, and I took 10,000 samples when the sample size was equal to 50. And you can see now that these sampling distributions resemble bell curves, whereas the population distribution is uniform. So again, regardless of the population distribution, this distribution of sample means is going to be approximately normal, and it's going to be more normal at larger sample sizes. Now, the issue here, though, as you can see in these comparing these two sampling distributions of means, is that the sampling distribution also varies as a function of sample size. So it's not just the relative shape or the relative normality of these curves, but you can see that when I have a sampling distribution of 10, it's much wider than when I have a sampling distribution of 50. When my sample size was 50, the distribution of sample means was much closer. Almost all of the sample means were quite close to 100. When my sampling distribution was 10, I had a few samples where the mean was below 50 or above 150. So when my sample size was only 10 individuals, the mean was fluctuating pretty wildly and was not necessarily a very good representation of the population mean. Now, it was unbiased, right? It was, I have an equal mass above and below the population mean, so it's still an unbiased estimator, but it's not necessarily a very good representation because I get a more variability when my sample size was 10. So we can actually calculate this more formally, and in lab we'll demonstrate this a little more concretely. But the standard deviation of this distribution is a special case of the standard deviation that we refer to as the standard error of the mean, right? So I could take a standard deviation for when n is 10, and I could take a standard deviation when n is 50, and I'm going to get something we call the standard error. And the standard error is just the standard deviation for a sampling distribution of, and if it's the standard error of the mean, it's the standard error for the distribution of means. So it's often written as SE, but it's equally valid to write this as sigma sub x bar, right? So it's a standard deviation of sample means. And it has a mathematic relationship to the standard deviation in the original population, which is represented here by sigma. And the standard error is simply sigma divided by the square root of n, which is to say that the standard deviation of the population, right, the standard deviation of these bars over here, and I divide that by the square root of the sample size that I am taking, right? So it'd be sigma divided by the square root of 10 in this case, or sigma divided by the square root of 50 in this case. And that is going to give me the standard deviation of each of these distributions. Okay, so that is why this one gets proportionally smaller and a tighter distribution, because I'm dividing by the square root of 50 rather than the square root of 10. So I actually have much less variability when I have larger sample sizes in that distribution of sample means. The other issue, though, is that you'll recall from our previous video lectures and what I said a couple slides ago, is that the distribution of sample means is only approximately normal. And that feels a little wishy-washy at the moment. So we need to talk about, okay, how approximately normal is it? Well, the answer is that that changes as a function of your sample size. So when n equals 3, I'm going to get a distribution of sample means that looks something like this. When n equals 10, it might look like this. N equals 50. And then if I had a theoretically infinite sample size, it would look like this gray bell curve here. And you can see that 50 and positive infinity look pretty close. Those are generally overlapping with each other. 10 is a little bit different, and 3 is very different. And specifically, we are losing a density here in the middle, and we're adding that density out onto the tails. So in smaller sample sizes, extreme values are more common, either above or below, right? So when I only have sample sizes of n equals 3, I'm more likely to get a weirdly big or a weirdly small sample size because I only have 3 observations. So if I get even one really big or one really small score, that's going to throw off my estimation of the mean. In contrast, if I have a sample size of n equals 50, getting one really big score is balanced against 49 more modest scores, or one really small score is balanced against 49 more modest scores. So outliers have much less of an influence there. The distribution of sample means looks much more normal once we hit about n equals 50. And then it's going to be perfectly normal when n equals, at a theoretical limit when n equals positive infinity. So this is how the sampling distribution of means changes as a function of sample size. And this is a new distribution for us, and this is something known as the t-distribution. Its shape is very similar to the normal distribution, but the difference is that the t-distribution varies as a function of the sample size. When n is infinite, the t-distribution is normally distributed. As n gets smaller and smaller, the t-distribution gets fatter and fatter tails. So it accounts for the fact that we're going to get more and more extreme observations when our sample sizes get smaller and smaller. So that's the relationship between the t-distribution and the normal distribution. And we can use the t-distribution in much the same way, right? So as we calculated z-values before to find the probability of a particular event, we can calculate t-values that will tell us how far a sample mean is away from the true mean in units of standard error, right? So now, again, we're talking about not individual data points, but about sample means. So we're not talking about the standard deviation of a variable, but we're talking about the standard error of the distribution of sample means. So to show you the formula, right, we have a t-distribution where we have t is equal to x minus mu, right? So it's the observed mean minus the population mean divided by the population standard deviation over the square root of the sample size. So we can calculate t-values in exactly the same way that we calculated z-values before. It's just now we have to remember that the standard deviation we're talking about is actually the standard error. Now, one issue we're going to face, though, is that the population standard deviation is often unknown. We usually don't really know what sigma is. So in those cases, we're going to need to estimate sigma using the standard deviation that we observed in the sample. So rather than having sigma divided by the square root of n, we're going to have s divided by the square root of n. So it's the standard deviation that we observe in the sample divided by the square root of the number of observations in that sample. And in lab, we will show you exactly why we can use S in this way. It's also discussed in the chapter, but S is an unbiased estimate of sigma if we divide by the appropriate degrees of freedom. We'll run some simulations and walk through the proof to show why this is the case. But for now, let's just use this formula, right? So we have a formula of estimating T when sigma is unknown. Now, we can use this formula for the t-distribution when observing a sample mean in a sample size of n equals 10. So using our hypothetical intelligence test again as an example, now we're going to say we know that the mean of this score is 100, but let's say that we didn't actually know what sigma was, right? So we don't have an estimate of sigma. We will get a sample mean of 115, and the standard deviation within our sample is 30. So these intelligence test scores varied by quite a bit inside of our sample. We can use those to first calculate a standard error, right? So the standard error is our estimate of the population standard deviation divided by the square root of our sample size. That gives us 9.487. Okay, so we divide 30 by the square root of 10, we get 9.487. From there, we can actually calculate the t-value that we would observe on these data by taking the mean that we observed minus the population mean divided by the standard error. And if you do 115 minus 100, you get 15. Divide that by 9.487, you get 1.581. So we can get a t observed value when we have 10 observations in our data. And we can then derive a t distribution when we have 9 degrees of freedom. So the degrees of freedom for this are just the number of observations minus 1. But you can think about this as either we have 10 observations or this is the t distribution for 9 degrees of freedom. But when we only have those 9 degrees of freedom, this is the particular shape of this t distribution. And it looks fairly normal, but remember at small sample sizes, it's going to have thicker tails than the normal distribution does. So even though this is a bell curve, it is not a normal distribution. It is a t distribution, but we can still use it in the same way and draw a critical value at that 1.581, right? So that's that dashed red line here. And then we can calculate the probability of observing a sample mean that extreme or more extreme in a sample of 10 people. And what we find if we integrate and solve for the probability of getting a t-value of 1.581 or greater is the p-value is 0.074. So we would expect to observe a t-value of this size or greater about 7.4% of the time due to sampling variability alone when the sample size is n equals 10. So if I found that my sample had a mean intelligence of 115, that's not super unusual given what we know about the distribution of intelligence in these data, right? We wouldn't assume that there's anything systematic necessarily going on. This sample mean could have arisen due to sampling variability alone if we assume, that we have a mean score of 100. Now, let's turn our attention to a case where we have a sample size of n equals 50. Okay, so again, we're going to have a mean score of 100. We're going to assume that sigma is not known. We observed a sample mean of 115, but now we have a standard deviation of 30. So we're going to calculate our standard error and our t-value in exactly the same way, right? So the standard error, which is the standard deviation for the sampling distribution of means, can be calculated by taking the standard deviation of the data, right, which is 30, divided by the square root of n, which is 50. That leaves us with 4.243. To then calculate the t-value, I take 115 minus 100, divide that by 2.243. I'm left with a t-value of 3.536. Okay, so this is a larger t-value, and if we were to plot the t-distribution when we have 49 degrees of freedom, because again, the degrees of freedom for our t-distribution are n minus 1, it's going to look something like this. And this is actually more normal than the previous distribution, right? Again, it's hard to always see those things, but with an N of 50, this is actually much more normal, with a greater density of scores around the mean and thinner tails than when we only had N of 10. And you can see that our t-value is now also much more extreme, so we're drawing that dashed red line at 3.536, and we're calculating the area in the upper tail, right, the area under the curve to the right of that cutoff, and that happens to be very, very small, right? So it's a probability of 0.00045, and we would expect to observe a t-value of this size or greater than less than 1% of the time due to sampling variability alone when the sample size is n equals 50. So this then is very surprising, right? We would not expect that when we had a sample size of n equals 50 that we're going to get a mean of 115. Right? This does seem statistically unusual given what we know about the mean and the standard deviation for these data. So this would raise some interesting questions, right? Now, could this happen just due to sampling variability alone? Yes, it certainly could. The sampling distribution includes that value, right? This isn't an impossible value due to sampling variability, but it's statistically very unlikely to occur just due to sampling variability. So we would conclude that maybe there's something else going on here, right? Maybe have I inadvertently sampled a pocket of the population with very high intelligence, right? Is this group statistically different from the general average of 100? So by being able to understand those distributions and then calculate the probabilities that correspond to those distributions, this allows us to make inferences about the likelihood of an event given a certain set of assumptions. And this is very powerful when it comes to drawing conclusions from our data. For instance, we can generalize this t statistic to take a form something like this. So we'll have our t observed value, and we refer to this as t observed because it's what we saw in our sample. And we might get something very different if we took a different sample, right? So it's good to kind of refer to this as t observed to dissociate it from other t values we might calculate. And this tells us how far away some estimated value is, right, from a hypothetical value. So if we have beta hat, right, is our estimate of beta, right, we're looking at our data to try and make some estimate of a parameter in the population. Beta is the true parameter, so beta hat is our estimate of that parameter that we're drawing from our data. We then get beta sub h, right, which is the hypothetical value. So we're saying this is the hypothetical value of beta in a certain circumstance, right? So often this might be what we expect under a particular hypothesis. So for instance, in the case of fair dice rolls, right, we would say that this is the expected value of rolling a 6-sided dice, or this is the expected value of rolling a 20-sided dice. And we would say, if this dice is fair, what is the hypothetical value we should get on average? And then with that would be the true beta. But this can also take on other hypothetical values that we might be interested in. So for instance, we might assume that the mean resting heart rate is 68 beats per minute for healthy young adults. And what that then would mean is that we're assuming, right, that beta sub h is 68. We're saying that out in the population, we think the true resting heart rate for healthy young adults is 68, and we're going to compare the value that we observe in our data to that value. And we will compare it by a yardstick of standard errors. So if we can calculate a standard error of beta in our sample, we can then look at the distance between our estimated value and the hypothetical value in units of standard error to get a t observed. And that will tell us how consistent or how compatible is what we observed with our hypothesized value. Because if it's unlikely, given the hypothesized value, we might conclude that this isn't due to sampling variability alone, and we think there's something else going on here. If this value, if our estimated value is entirely consistent with the hypothesized value, right, and this is maybe only half a standard deviation away from each other, we might say, yeah, that could easily occur by sampling variability alone. Right? So we can't rule out the fact that there might be something going on there, but what we're seeing is consistent with sampling variability. So let's think about that example where we have a hypothesis based on real data, but I'm going to say this is a hypothesis, right, that the mean resting heart rate is 68 beats per minute for healthy young adults. If we observe a heart rate of 60 beats per minute in a random sample of young adults, how likely is it that result occurred due to sampling variability alone? And the answer is It depends, right? It depends on how large our sample is and how much variability there is in our sample, because that standard error is really the standard deviation of the data divided by the square root of n, right? So the same difference could actually lead us to some very different conclusions. If we assume that the standard deviation was 12 and we only took a sample of 5, then t observed is going to be negative 1.49. Right? It's a negative t-value because 60 is less than 68, and it's 1.49 because I'm taking 12 divided by the square root of 5, and 8 divided by that gives me negative 8 divided by that gives me negative 1.49. So that's not a very extreme t observed value. Similarly, if we assume that sigma is 12, but now n is 20, right, that's going to make that denominator larger because now it's 12 divided by the square root of 20 to give us the standard error. And that actually leads to a t-observed value of negative 2.98. So that's a more negatively extreme t-observed value. And without calculating the specific probabilities, you should hopefully recognize that that is less likely to have occurred due to sampling variability alone. So we're going to be more likely to conclude that this just didn't arise just due to sampling variation if this is what we got. Whereas if this is what we got, we could say, well, this might be due to sampling variability. And again, sort of the practical reason for that is that when my sample size is very small and my variability is, proportional to this difference here, one extreme score could pull that mean down. So it's not going to be unlikely to get extreme positive or negative means in very small sample sizes. But it is going to be less likely to get those extremely positive or negative means as my sample size gets larger, right? So we can see how these different factors affect how surprising what we observe really is, right? The surprise value depends on the size of the effect, the variability of the data, and the size of our sample. Because remember, as t observed gets more extreme, either in the positive or negative direction, it's less likely to have occurred due to sampling variability alone. And the factors that then affect that t observed value are the numerator, which tells us the size of our effect, right? How different what we observe is from what was hypothesized, relative to the standard error, right? How much do we really expect means to vary from sample to sample? And that standard error is calculated based on the standard deviation of the data and the size of the sample. So large effects, small variability, and large samples all lead to big t-values. Small effects, large variability, and small samples all lead to small t-values, right? And so then there are lots of trade-offs then in what we have to study. So if we expect an effect to be small, we probably need a lot of data in order to see it reliably. But if we expect an effect to be large, we might need a lot less data in order to see it reliably. But again, the main point of all of this is, beyond getting you guys to see the formula for a t-statistic and learn a little bit more about how to calculate it, is help to develop some of your intuitions about how we can actually use these known sampling distributions to then make inferences. Because if we had access to all the data, it would be easy to calculate probabilities. We just look at the proportion greater than a certain value compared to the total set of numbers and say, what's the probability? But we don't ever have access to that whole population. So we have to make certain assumptions about the way data are distributed, and then we can calculate probabilities based on those assumptions. And we know that due to the central limit theorem, that if we take sample means, we're going to get distributions of sample means that follow the t-distribution. And this then is very, very powerful because it allows us to make statements about the probability of observing a sample mean even if we don't have access to all the data in the population.